Welcome back to the Deep Dive. Today we're taking quite an intellectual plunge, not into a specific event, but really into the cosmos itself.
That's right.
Our source is Stephen Hawking's classic, the 1988 masterpiece, A Brief History of Time.
Yeah, this is a bit different for us. We're looking at probably the most successful attempt ever to explain, fundamental cosmology to everybody.
To a general audience, yeah.
Our mission here is to pull out the core ideas, the science, the philosophy about the universe's origin, its structure, its fate. Basically what made this book so revolutionary.
And the impact. I mean, it really speaks for itself, doesn't it?
Absolutely.
Taking these incredibly complex ideas, general relativity, singularities, quantum foam, and somehow making them part of a global conversation. Millions of copies sold, what, over 40 languages?
Over 40, yeah. It just shows people really do want to know how the universe works.
That appetite is there.
It really is. And it's proof that a good story, even one about, mind-bending physics, can capture the imagination. Hawking showed that the laws are knowable, even if we don't know them all yet.
Okay, let's start unpacking this. Foundational laws first, the big picture stuff. Hawking really builds on Einstein, doesn't he?
Oh, completely.
So what are the key things about gravity, space, and time we need to get before we, get into the really deep end?
Right. Well, first, you have to grasp space-time. Einstein's general relativity showed gravity isn't a force like, say, magnetism. It's actually geometry.
Geometry?
Yeah, it's the effect of mass and energy warping the fabric of space-time. The classic analogy is a bowling ball on a trampoline.
Okay.
It makes a curve, right? And anything rolling nearby follows that curve.
That curve is gravity.
That curve is gravity, and understanding that directly points us towards the universe's beginning.
Ah, because if space-time can be bent and warped, then imagine squeezing all the universe's energy into one tiny point.
Exactly. The math of general relativity predicts that if you run time backwards, the universe must have expanded from an initial point, a singularity.
The Big Bang.
The Big Bang. That was pretty much the accepted view when Hawking wrote the book. And critically, it wasn't just theory. Hawking pointed to the evidence, especially the cosmic microwave background radiation, the CMB.
That faint glow everywhere?
Precisely. It's like the echo of the Big Bang.
Yeah.
Proof of that initial hot, dense state.
Okay, so the structure is tied to this geometric start. Now, let's talk about maybe the most famous consequence of that geometry, something Hawking really brought into the public eye. Black holes.
Right.
What makes them so unique, so extreme?
They are really the ultimate stress test for general relativity. A black hole is just a region where gravity is so intense nothing can escape, not even light.
The point of no return, the event horizon.
That's it. Cross that and you're trapped. All the information about what fell in just seems to vanish into the central singularity. It's like a complete breakdown of space-time as we know it.
Or at least that was the understanding. Until Hawking himself came along and threw a spanner in the works.
He really did.
Black holes weren't necessarily eternal prisons after all.
That's the mind-blowing part. Hawking radiation. This was his attempt to connect general relativity, the physics of the very large, the black hole itself, with quantum mechanics, the physics of the very small.
Okay, how does that connection work? It sounds impossible.
Well, the idea involves virtual particles. Quantum mechanics suggests that pairs of these particles are constantly popping into and out of existence everywhere, even in empty space, borrowing energy from the vacuum for a tiny instant.
Okay, virtual particles, constantly appearing and disappearing.
Usually they just annihilate each other almost immediately, gone. But right at the edge of a black hole, at the event horizon, things get weird.
How so?
One particle from the pair might fall into the black hole while the other escapes out into space.
Ah, so one gets trapped, one gets away.
Exactly. And the one that escapes becomes a real particle. It carries energy away, but energy can't just come from nowhere.
So it must come from the black hole itself.
Precisely. The escaping particle essentially takes a tiny bit of the black hole's mass energy with it. So over incredibly long timescales, the black hole actually loses mass. It shrinks.
It evaporates.
It slowly evaporates, eventually disappearing completely.
Okay, wait, that causes a huge problem, doesn't it? I mean, if the black hole disappears and it only emits this random thermal radiation, What happens to all the information about the stuff that fell in, like the specific properties of the particles? Quantum physics says information can't just be lost.
You've nailed it. That's the information paradox. It's still a massive headache for physicists today and a key part of the book's legacy.
A direct conflict between the two pillars of modern physics.
Exactly. If information is truly lost, it breaks a fundamental rule of quantum mechanics. It really highlights this deep incompatibility between our theory of gravity and our theory of the quantum world.
Perfect transition. We've been talking big-scale gravity, black holes, the universe governed by general relativity. Now we need to zoom way, way down.
To the microscale.
To the weird world of quantum mechanics. QM.
And it is weird. Fundamentally different. It's all about probabilities. You can't know exactly what will happen, only the chances of different outcomes.
Like Heisenberg's uncertainty principle.
Exactly. Hawking explains that you can't measure, say, a particle's exact position and its exact momentum at the same time. The more you know about one, the less you know about the other. There's an inherent fuzziness baked into reality at that level.
So you have general relativity, precise, deterministic, smooth space-time for the big stuff. And then quantum mechanics, fuzzy, probabilistic, jumpy for the small stuff.
That's the core tension.
And they just don't play nicely together, especially in extreme places.
They really don't. Try to combine them mathematically, like near a black hole singularity or at the Big Bang itself, and the equations tend to break down. You get infinities, which basically means the physics is telling you something's wrong here.
The theories are incomplete.
Right. And QM suggests that at the tiniest scales, the Planck scale, space-time itself isn't smooth like Einstein thought, but more like a turbulent, bubbling quantum foam that directly contradicts the smooth geometry needed for general relativity.
And resolving that contradiction, that clash, is the driving force behind the ultimate goal Hawking discusses. The theory of everything, the TOE.
The TOE, the holy grail of physics, you could say.
What would it actually do, this theory?
The ambition is huge. It's to merge gravity with the other three fundamental forces, electromagnetism, the strong and weak nuclear forces, into one single, elegant mathematical framework.
One equation to rule them all.
Sort of, yeah. A theory that could explain everything, from the universe's birth to why particles behave the way they do. One coherent set of rules for all of reality.
Okay, and pursuing this TOE led Hawking to some of his most, well, mind-bending ideas in the book, didn't it? Trying to describe the universe without needing a starting point.
You're talking about imaginary time.
Imaginary time? This is where it gets really tricky.
It is perhaps the most abstract concept, but maybe the most profound. See, Hawking was bothered by that Big Bang singularity, that initial point.
Why? Because it's a point where the laws break down.
Exactly. It represents a boundary, an edge to space-time. And if there's a boundary, you need something or someone outside to explain it, to set things in motion.
The creator question.
Right, the need for an initial cause. To sort of sidestep this boundary problem, Hawking used a mathematical technique. He introduced time measured using imaginary numbers.
Like the square root of -1. That kind of imaginary.
That's the one. It sounds strange, but mathematically, in this imaginary time, the distinction between time and space sort of dissolves. They become geometrically equivalent, like different directions in space.
So, what does that mean for the universe's origin? Treating time like space.
The implication is stunning. In imaginary time, the singularity, it vanishes. It's smoothed out. The universe, viewed through this mathematical lens, doesn't have a beginning point, no edge, no boundary.
Like the surface of a sphere. Finite, but unbounded.
Precisely. That's Hawking's no-boundary proposal. If the universe can be described this way, as self-contained, you don't need an external cause or a specific starting moment. The question of what happened before the Big Bang becomes meaningless, like asking what's north of the North Pole.
Wow. Okay, so the universe just is governed by laws, but without needing that initial fuse to be lit.
That's the radical idea. It shifts the focus from who created it to what are the laws that allow a universe like this to exist. If the laws are complete and the universe is self-contained, then maybe science can provide a complete explanation.
That is a deep philosophical shift.
It absolutely is, and it connects to another big theme, the arrow of time.
Why time only seems to go one way for us, forward.
Yeah, it seems obvious, right? Broken eggs don't unbreak. But the fundamental laws of physics, mostly, don't care about the direction of time. They work just fine running forwards or backwards. So why the difference in our experience?
It has to do with disorder, entropy.
That's the link. The second law of thermodynamics. It says that in any closed system, entropy, which is basically a measure of disorder or randomness, always tends to increase.
Things naturally go from ordered states to disordered states.
Exactly. The universe started in a very ordered, low-entropy state, the Big Bang, and has been expanding and getting more disordered ever since. We experience time moving forward because we live in this unfolding process. We remember the past, more ordered, but not the future, more disordered.
And Hawking connects this arrow of time to the universe's ultimate fate, expansion versus collapse.
He does. He explores whether the universe will expand forever, getting colder and more disordered until a final heat death. Or if gravity might eventually pull everything back together in a big crunch.
A reversal of the Big Bang.
Potentially, yes. Though the evidence now strongly suggests ongoing expansion. But the key point remains. The universe's history and fate seem dictated by these discoverable laws, including thermodynamics.
Which brings us back to that philosophical undercurrent throughout the book. The role, or maybe the non-role, of a creator. Yeah. His conclusion seems pretty clear. Understanding the laws makes invoking divinity unnecessary for explaining the universe's existence.
Essentially, yes. He famously suggested that if we found that theory of everything, the TOE, we would, in a sense, know the mind of God.
But not in a religious way.
No, not theologically. More like we'd understand the complete blueprint, the fundamental operating system of reality. The laws themselves provide the explanation. Understanding is the ultimate achievement.
It's that mix, isn't it? Humility about our place in the cosmos, but immense confidence in our ability to figure it out.
That's captured so well in that quote people always remember. We are just an advanced breed of monkeys on a minor planet of a very average star, but we can understand the universe. That makes us something very special.
It really does encapsulate the whole feeling of the book. But let's be honest, while it was a bestseller, it's also famous as the book everyone bought but few actually finished. It's not exactly beach reading. What makes it challenging, despite avoiding equations?
Well, even simplified, the concepts are inherently abstract. General relativity, quantum mechanics. They operate outside our everyday experience.
Imaginary time, singularity.
Exactly. You really have to engage with the thought experiments, the analogies. It requires a certain intellectual effort and willingness to grapple with ideas that might feel counterintuitive.
It rewards the effort.
But immensely. If you want that sense of awe, if you want to touch the edges of what we know about reality, it's absolutely essential. It's about facing the biggest questions without flinching.
So we've gone from the Big Bang singularity, traced the curve of space-time, peered into black holes and the information paradox, touched the weirdness of quantum rules, and reached for that ultimate theory of everything. A universe potentially without boundaries.
It's quite a journey. And that quest, that desire to find the complete set of rules, the TOE, it ties into something else Hawking said, reflecting on his own life challenges. However difficult life may seem, there is always something you can do and succeed at. So here's a final thought. If we did achieve a theory of everything, if we truly understood all the fundamental physical laws, would that ultimate comprehension somehow make the chaos and difficulty of individual human life seem less fundamental? Or would knowing the grand rules just shift our focus, making the complexity lie not in the laws themselves, but in figuring out how those simple laws lead to the incredibly complex, messy, difficult reality we actually experience day to day? Does understanding the blueprint limit the building's possibilities, or just highlight the intricacy of its construction?
Does knowing the rules make the game simpler, or just reveal how complex playing it well truly is? A fascinating question to ponder. The more we know about the universe, perhaps the more profound our own small corner of it becomes. Until the next deep dive, keep looking up, keep questioning.